All right, so today we're going to talk about inverse functions, and let's get some definitions down first. So an inverse function is a function that undoes the action of another function. So remember when you were in Algebra 1 and your teacher used the words that you want to use inverse operations to isolate a variable. So if you're adding, you subtract. If you're originally multiplying, you divide, and so on. We're doing that, but we're going to do that to functions, and we'll get into some examples soon. So the concept here is that when you do an inverse function, what happens is that the inverse function has all the same ordered pairs of the original function, except the x and y values are switched. So here's the deal. Not all functions have an inverse. You know how not all relations are functions, and relations that are not functional have repeating x values. In other words, you have an x value for which there's more than one output. So an inverse function, again, is kind of the opposite of that. Instead of having no repeating x values, it ends up having no repeating y values. And if you remember from your Algebra 1 class, if you want to tell if a relation is a function, you use the vertical line test. Well, if you want to tell if a function is one to one and therefore has an inverse, you can use a horizontal line test. So everything is opposite with inverse functions. Just keep that concept in mind. So for the first four examples here, all we're doing is identifying whether the following functions have inverses. In other words, we want to see if the functions are one-to-one. Remember, we're looking for repeated output values. And I want you to notice for this first example, there's a repeated 3 for your y values. So this function does not have an inverse because it is not one-to-one. So here, if we look at all of our output, our y values, none of them are the same. So we would say that this function does have an inverse, that yes, it is one-to-one. For example 3, remember, it's the opposite of just identifying functions. So instead of doing a vertical line test, we would do a horizontal line test and look for a place on the graph where that horizontal line crosses more than once. And we have an example of that happening there. So what that means is that this function does not have an inverse because it is not one-to-one. And finally, notice no matter where we draw a horizontal line on this graph, the horizontal line only crosses in one place. So because of that, we would say that this function is one-to-one, and then we could do the inverse of it. Okay, so moving on. I'm going to let you guys, hopefully what you'll do here is pause the video and identify which of the functions in that box have inverses. In other words, which ones are one-to-one. All right, so hopefully you pause this and you have it done. So let's check our work. I want you to notice for that first example, we have 1 paired with 4, and we have 3 paired with 4. So notice we have a repeated y value, so that one is not one-to-one. Here, for that second example, we could draw a horizontal line, and nowhere on the graph does it cross more than once. So this one is a one-to-one function, so therefore it has an inverse. Here, we've got a horizontal line that crosses more than once, so that's a no. For the table, notice you don't have any numbers repeating in your output column, so this is one-to-one. For the ordered pairs, we have a 7 repeating, so that is not one-to-one. And then finally, if we look at this, remember back to our quadratics and even further back into transformations. If we graphed this, it would be the parent function for a quadratic, but it'd be shifted up 9 units, so it would look something like that. And a horizontal line would cross more than once. So not one-to-one, so it doesn't have an inverse function. Now what we're going to do is we're actually going to find inverse functions. I've got a little sidebar here. What do we do to find an inverse function is we just switch the x's and y's. If you're dealing with an equation, after you switch the x's and y's, then you're going to actually solve for the y. So for the first one, all we're going to do is reverse the x's and y's. So instead of negative 3, 7, it's going to be 7, negative 3. Instead of 5, 1, it's going to be 1, 5. Instead of 8, negative 1, it's going to be negative 1, 8. And instead of 6, negative 2, it's going to be negative 2, 6. And that's your inverse function. So not too hard there. Now let's do an equation. So remember, f of x is the same thing as y. And what do? We're going to swap your x and y values. So instead of y is equal to 3x minus 9, we're going to have x is equal to 3y minus 9. Now we're not going to leave it that way. We want to go ahead and solve for y. So we're going to use our Algebra 1 skills here to isolate our y value. So at this step, we have x plus 9 is equal to 3y. And then we're going to divide both sides by 3 and find that y is equal to, you can either say x plus 9 over 3, or you can say 1/3 x plus 3 if you want to leave that in slope-intercept form. Now your final answer needs to be written like this. Originally it was f of x. If we want to find the inverse of a function, the way you note it is f and then a subscript of -1 x is equal to, and then I'm going to go ahead and use the slope-intercept form of the equation there. Now, key here, this is not a negative exponent. So in function notation, just like when you learned in Algebra 1, that's not f times x. So the formal notation, it doesn't follow the rules of what you usually do with variables. So normally two variables right next to each other like that would mean multiplication, but it doesn't with function notation. And here, normally a negative exponent would mean that you have to do some reciprocating, but that's not true for inverse functions. That negative one is just denoting that that it is an inverse function. Okay. So moving on to example 8, we're going to do part of examples 8, 9, and 10, and we're going to move forward, and then we're going to come back because there's a part that I think you'll understand more once we finish some other concepts. So first, we're going to just find the equation for the inverse function. Now, I want you to notice what we've done here. If you have g of x is equal to x squared plus 3, think about what that looks like. It's a quadratic function, and it's the parent function that's been vertically shifted up 3 units. The reality is that as the function is written, it's not going to have an inverse because it doesn't pass that horizontal line test. Well, the way you fix that is by restricting the domain. So if you notice here that if we restricted the domain to where x is only less than or equal to 0, what that does is it takes off the positive part of the parabola and only leaves you with that negative part. So now we can do the inverse function for that. So the reality is if we want to do an inverse function and the original function is not a one-to-one, then you just restrict the domain to make it a one-to-one. So let's go ahead and do that process. Remember, we're going to swap the x and the y. So instead of y is equal to x squared plus 3, we're going to say x is equal to y squared plus 3. Now we isolate our y value, so we're going to subtract 3 from both sides. So we'll have x minus 3 is equal to y squared. We want to continue isolating our y value, so we're going to take the square root. And remember, when we take the square root, initially we're going to have a positive and a negative root. And here's the deal. We're not going to have, because this domain right here has been restricted, we're going to end up eliminating either the positive or the negative root right there. So this is what we're going to come back to, is trying to help you understand how to determine whether the final inverted function is going to be the positive root of x minus 3 or the negative root of x minus 3. So hang tight, we're going to come back to that, but let's go ahead and write this again in formal notation. We started off with g of x, so now we're dealing with a g with the superscript of negative 1 is equal to, and then tentatively positive and negative square root of x minus 3, but we're going to come back and we're going to eliminate either that positive or the negative one. So hang tight and we'll finish that one fully in just a minute. Okay, so next one right here is we've got y here is equal to an x plus 2 squared. Again, this is a quadratic, so quadratics have to have a restricted domain in order to be one-to-one so we can find the inverse. So we've restricted the domain to x minus 2. To find just the inverse function, we're going to swap out the x and the y, so it's going to be x is equal to the quantity y plus 2 squared. Now we solve for y. So we're going to square root both sides to get rid of the square. When we do that, we're going to initially have the positive and negative root of x, and then is equal to y plus 2. And now we continue isolating y by subtracting 2. So we end up with y is equal to plus or minus root x minus 2. Now again, we're going to eliminate either the positive or the negative root right there, so we're going to come back to it. So initially what we have so far is that the inverse of g of x is equal to either the positive or negative root of x minus 2. And finally, again, this is our y value, so we're going to swap our x and y. Now notice this one doesn't have a restricted domain because remember, square root functions, the parent function looks like this. So all that's happened here is there's a plus 1 inside the function. So all that's happened is that this has been translated back 1 or to the left 1. This is one-to-one, so we don't have to restrict the domain, at least on the original function. So here we're going to do x is equal to, instead of x plus 1 here, we'll put y plus 1. Now if we want to undo a square root, what do is square it. So now we have an x squared is equal to y plus 1, and subtract 1 from both sides, and we find that y is equal to an x squared minus 1. And formally, since it started off as h of x, then the inverse is h with that superscript of negative 1 of x, and then x squared minus 1. Now, think about this. This inverse is not going to be one-to-one. So we're going to need to restrict the domain on that one later. So again, we're going to come back and finish those 3 examples after we move on. Okay, so now let's look at the graph of inverse functions. So that first one, it's actually taking the same function rule that we did on example 7, and both of those graphs are, or both of those equations are graphed. So I want you to notice how those look. And then we'll move on to the second one, which was also on the previous page, and I want you to look at how those 2 graphs look. Think about, in terms of transformations, what has happened to go from the red functions to the blue functions. And here's a hint. It's a result of a reflection. And the question is, what is it a reflection across? Well, hopefully you're looking at this and you can see that it's actually been reflected across this diagonal line. And the same is true for the other one. The blue function is the result of a reflection across that diagonal line that passes through the origin. It's the linear parent function. So it's reflecting across the line y is equal to x. And hopefully that makes sense, because what are we doing? We're switching out x's and y's. So the original y's became the x's, the original x's became the y's. So keep that in mind when you're thinking about functions and inverse functions, is that the inverse function is always a reflection across that line. Let's look at the domain and range for that original red line. Notice the domain, the leftmost point part of that graph is at 0, and then this arrow denotes that we're going to go on forever. So the domain for f of x is 0, and it's including 0, so we need brackets and then to infinity. And then the range, notice the lowest part of that graph is at -9. -9 is included, so we need brackets, and then the arrow means it goes on to forever to positive infinity. Now if we look at the blue function, look at the domain. The leftmost point is at -9, and it keeps going forever to the right, so -9 to infinity. And the range, the lowest point is at 0, and it keeps going in the positive direction towards infinity. So bracket 0, comma, infinity. I want you to notice what happened there. If we do it here, so for my red function, our domain goes from 0 to infinity, and the range goes from 3 to infinity. So maybe you can predict what the domain and range for the inverse of g would be. The domain goes from 3 to infinity, and the range goes from 0 to infinity. So what's the rule? The original function's domain is the inverse function's range. And vice versa. The original function's range is the inverse function's domain. So if we were to look at example 11, it says if the domain of h of x is 3, 197 and the range is -42.8, what is the domain and range of the inverse of h of x? Well, all we got to do is reverse them. So the domain of the inverse is going to be the range of the original, and the range of the inverse is going to be the domain of the original. Okay, so we're going to go back to those 3 examples, and I just want you to remember that inverses are always reflections across the line y is equal to x. Okay, so here, let's go back to examples 8, 9, and 10, and I'm going to switch over to Desmos. Okay, so this is example 8. If you'll see, our original function, I didn't put in g of x, I put in just a y in place of that. So don't get tripped up by that. So this is our original function. Notice we restricted the domain to only the negative side of the parabola. So the whole thing would have continued over here. So now the question is, we're going to have to decide whether the inverse of that function is the positive root or the negative root. So I want you to look at how these look. If we do the positive root, I want you to ask yourself, is that a reflection across the line y is equal to x? And hopefully you go, no, it's not at all. But if you look at the negative root, notice if I drew a line right here, then the green function is a result of a reflection across that line. So now if we go back to here, for example 8, we need to only include the negative square root for that function. I want you to also notice the connection here. this domain is negative, or is it less than, x is less than, it's the negative side of the parabola, so it needs to be the negative root for that square root function, okay? Let's go on to the next one. So this is example 9. So here's our original function. It was g of x is equal to the quantity x plus 2 squared, and then we restricted the domain. Again, remember what that looks like. This is a quadratic function, and it was originally right here, but it's been moved to the left 2 units because of this. And then notice the domain is restricted only to that left side, or the negative side of the parabola. So again, hopefully we've got 2 options here. It's either the positive square root or the negative square root. Because we're doing the negative side of the parabola, there's the negative square root. So that means that the inverse function, look at the positive root. That's definitely not a reflection across the line y is equal to x. But this one is. So if we go back again to our example number 9, we want to, again, take off that positive root and only let the inverse be the negative root. And finally, so we start off with h of x is equal to the square root of x plus 1. So here's example 2. Here's our original function. Notice square roots don't have to have restricted domains here. So because they're already one-to-one in the beginning. So here's the question now. There's no like positive or negative square here, but the question is, what part of the domain is going to be included in the inverse function? Well, if we look at this original square root function was the positive one. So I would encourage you to take just a minute and think, well, which domain are we going to do? Are we going to do the one that's greater than 0 or less than 0? And hopefully you're thinking greater than 0 because it's positive greater than 0, negative less than 0. And let's check that by looking at the graph. Notice if we reflected the red function across the line, y is equal to x, we would in fact get that blue function. The other one, definitely not a reflection across y is equal to x. So if we go back to example 10, let's go ahead and we're going to restrict this domain to x is greater than or equal to 0. So big picture here, notice if your domain is restricted and it's less than, it's the negative side of the original quadratic, then you want the negative root. Here, it was x is less than 0, so we want the negative root. Here, if the original square root function is a positive and it's not been a reflection, then when we do our inverse, we want to do a domain that's restricted to x is greater than or equal to 0. All right, I will talk to you guys soon. Hopefully that made sense. Make sure that you jot down any questions you have so we can go over it together.